Welcome to this applied remote sensing training on the application of Earth observations to assessing waterborne disease risk. My name is Amita Mehta from ARSET, and I will be conducting this session on overview of monitoring waterborne diseases using remote sensing observations. We will start with a brief introduction to ARSET. ARSET is part of NASA's capacity building program, and it provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools for societal applications. ARSET provides trainings on these thematic areas listed here. And trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experience levels. ARSET trainings are online, or they're also in-person trainings offered. They are live and instructor-led like this one, or there are also self-paced asynchronous trainings available from ARSET website. They're cost-free. There are bilingual and multilingual options available. Most of our training material is available in Spanish. Certain trainings are also conducted in Spanish, and there are other options available such as French. We only use open source software and data and accommodate differing levels of expertise. We'll start with an overview of the application of Earth observations to assessing waterborne disease risk. Waterborne diseases, they're defined as the U.S. Centers for Disease Control, or CDC, as diseases which are spread through exposure to infectious pathogens from water. These can include outbreaks of respiratory, skin, intestinal, or other types of illnesses which are spread through either contaminated drinking water or recreational water activities such as swimming in water with poor water quality and consuming contaminated seafood harvested from contaminated water. And you can find more information at these references about general information about waterborne diseases. So with that, our overall training objectives are given here. So by the end of this training, we will be able to identify the factors that affect the presence of microbial contaminants in water, leading to waterborne diseases in which satellite remote sensing can improve risk assessment. Identify Earth observations used for monitoring key environmental factors relevant for assessing the presence of contaminants in drinking and recreational waters and risk of waterborne disease outbreaks. Finally, we will recognize how satellite observations are integrated with in situ water quality data to develop risk assessment models for waterborne diseases. In this, we will use cholera as an example. There is a prerequisite, Fundamentals of Remote Sensing, that provides explanation and description of concepts, remote sensing concepts of satellites and sensors, orbits, swaths, pixels, spatial and temporal resolutions, electromagnetic spectrum, spectral bands, and various data processing levels. We will be referring to some of these concepts throughout this training. The reasons why we want to understand and predict waterborne diseases, they're listed here. First of all, there is worldwide impact according to CDC WASH, which is Water, Sanitation and Hygiene. There are over 2 billion people worldwide. They lack access to safe drinking water, and about 1.5 billion lack basic sanitation facilities. And that leads to globally at least 1.7 billion people drinking water with microbial contamination, causing diseases such as diarrhea, cholera, dysentery, typhoid, and polio. Annually, more than 3 million deaths result from poor wash conditions worldwide, and diarrhea alone is responsible for approximately 1 million deaths, the majority of which are children under the age of 5. An example is shown here, which is mortality due to unsafe wash conditions, and this is for 2019. And what is shown here is the mortality rate per 100,000 population. As you can see, Africa has the largest mortality rate because of waterborne diseases. Then Southeast Asia, Eastern Mediterranean, Americas, Western Pacific, and Europe. Different countries are also shown here with respective mortality rates because of waterborne diseases. In the US, each year, pathogens transmitted through water cause an estimated 7.2 million cases of waterborne illness, about 120,000 hospitalization, and 6,600 deaths. And estimated cost to the US healthcare system is about $3.3 billion just because of the waterborne illnesses. As shown here, waterborne disease outbreaks between 2015 and 2020, they show outbreak cases ranging from more than 5 to more than 20. States such as Florida, Illinois, in these 5-year period had many outbreaks of waterborne diseases, and there are several other states which also experience waterborne disease outbreaks. So because of that, monitoring risk of waterborne disease outbreaks is crucial for protecting public health and prevent the spread of waterborne diseases. There will be 2 parts to this training. Today we will have an overview of monitoring waterborne diseases using remote sensing observations, and next session will be on 27th of March that will focus on using remote sensing based cholera predictive intelligence for intervention and mitigation. There will be one homework assignment that will be posted on our website on 27th of March, and the homework will be due by 10th April. Certificate of completion will be awarded to those who attend both live sessions and complete the homework assignment before 10th of April. With that, we'll start with today's session on monitoring waterborne diseases using remote sensing observations or earth observations. Overall objectives for today are that at the end of this session, we will identify diseases resulting from the presence of microbial contaminants, or referred to as pathogens, in waters, and identify earth observations used for monitoring key environmental parameters relevant for assessing the presence of contaminants in drinking water, leading to risk of waterborne disease outbreaks. We will have a brief overview of waterborne diseases, then how waterborne pathogens are monitored. Then we'll move on to overview of earth observations, which are relevant for inferring to waterborne pathogens. And then we will have a demonstration of data access, so how these earth observation data can be obtained by using NASA web tools, which are relevant for monitoring waterborne pathogens. Just a note about asking questions. There will be a question and answer session at the end of the webinar, so please put your questions in the questions box and we will address them at the end. Feel free to enter your questions as we go. We will try to address all of them today, but some, if we cannot, then we will answer those in the question and answer document, and that document will be posted on the training website about a week after the training. So we'll first have a brief overview of waterborne diseases. As we saw earlier from CDC, waterborne diseases are caused by pathogens in drinking or recreational waters, beverages, and food that comes from contaminated water such as fish and seafood. And pathogens, they are disease-producing microorganisms, and they include bacteria, virus, and parasites. So bacterium is a single-cell living microorganism. So many bacteria are good and they make up our microbiome, but many are bad and they cause diseases. Virus is a microorganism that needs a host, such as a human, animal, or plant, to reproduce, and they cause infection, as we know, for example, COVID-19. Parasites are microorganisms. They cannot live independently. They need hosts to survive and spread. An example is intestinal worms. Here is a microscopic view of pathogens coming from EPA. Some common waterborne diseases are listed here. Diarrhea, it can be caused by viral or bacterial infections from water and food, and can also result from food allergies. Dehydration resulting from diarrhea can be life-threatening, and particularly for young children. Typhoid, it's caused by Salmonella bacteria in water and food, and it's a highly contagious disease. Its regular outbreaks can be found in Southeast Asia and Africa. Cholera is caused by Vibrio cholera bacteria from contaminated water and poor sanitation, and deadly if it is not treated immediately. They're more prevalent in Southeast Asia and Africa, and recent outbreaks in Haiti and Middle East, they have also been noted. E. coli, they're caused by bacterial infection. Giardia, it's caused by parasites infecting intestine, and they're found in waters worldwide. Hepatitis A, it's caused by hepatitis A virus, and it's highly contagious liver infection. Polio is caused by a virus that mainly affects nerves in the spinal cord or brainstem, and high-risk areas are Africa, the Middle East, and Southern and Central Asia. Monitoring waterborne diseases, then it requires detection of pathogens in drinking water and recreational water as well. So conventionally, water samples are collected and then analyzed in laboratory to assess types and concentration of pathogens. And you can see an example here. Water sample collected from river shows E. coli in this scanning electron micrograph. There are several challenges in this process. Low concentration of pathogens in a large volume of water requires enrichment and concentration of the samples prior to detection processing. There is no unified method for collection and analysis that affects reproducibility of results. Differences in pathogen groups require different treatments, and inadequate spatial and temporal samplings is also a big problem. It's not very cost effective to collect water and analyze from so many water bodies and rivers which are used for recreational purposes and also where drinking water is collected from. In the US, CDC provides statistics about waterborne diseases via these two portals shown here. As you can see, specimen source here are from the patients or from the medical side of diseases. The BEAM is its bacteria, enterics, amoeba, and mycotics dashboard, and there is National Outbreak Reporting System. Here you can see this is by year, how many numbers were there, how many cases, by month. This is for Vibrio. You can select Salmonella and other pathogens as well, and you can look at the map of where the outbreaks occurred in the United States by each state. Now, it is not possible to have such information or database in other countries or other places where waterborne diseases are more prevalent. And therefore, the question we ask is, can pathogens be detected by using satellite remote sensing? There are several open source global satellite remote sensing datasets, as we will see later, and they have been used to monitor water quality in coastal and inland water bodies. What the satellite sensors do is they measure spectral signature of the water surfaces. And the figure is shown here. A few of the sensors are shown here. Current sensors are MODIS, WIRS, and OLCI. What you see here is that these sensors measure reflected sunlight from water surfaces from ultraviolet to shortwave infrared spectrum, which is the optical spectrum, and each sensor has discrete medium resolution spectral bands, and the number of bands of course vary with different sensors. Now, can these sensors detect pathogens? So the answer is yes and no. If the pathogens change color of the water, then they can be detected directly from the sensor observations. And examples are cyanobacteria and harmful algal bloom in water. But so many pathogens that we talked about, such as Salmonella or Vibrio, they cannot be detected by these medium spectral band observations from satellites. However, there are several environmental parameters that affect waterborne pathogens, and they can be monitored by using satellite data. These environmental parameters include water temperature, precipitation and flooding, nutrients and chemicals from agricultural and industrial runoff, chlorophyll, harmful algal bloom, dissolved organic matter, salinity, water currents and stagnation of the water surface, solar radiation, and biofilms, which is communities of pathogens attached to surface. And if you look at the list here, the highlighted parameters, they can be obtained from satellite data. So chlorophyll and harmful algal bloom and colored dissolved organic matter, they can be detected in water bodies from satellite sensors directly by looking at the images and deriving from that. Other parameters can be obtained from satellite observations or Earth system models in which satellite data are used. So the environmental parameters that we just saw available from satellite observations are weather, climate, and hydrology parameters. So combination of in situ and remote sensing data are used for monitoring, prediction, and risk mapping of pathogen occurrence and disease outbreaks. Conventionally, empirical relationships between disease incidence and relevant geophysical parameters are used to predict disease outbreaks, and you can find there are challenges and opportunities both in using remote sensing in looking at disease outbreaks. Commonly used parameters, they include water surface temperature, chlorophyll A concentration, land cover type, precipitation, and runoff. And what we are going to do next is look at a couple of examples where some of these parameters are used. Here is an example in which environmental parameters were used for non-typhoid Salmonella prediction. This is from Tech et al. Study conducted in Democratic Republic of Congo. And so NTS prediction study was conducted for children under 5 years of age admitted to hospital. And in situ data were used from hospital admissions and also blood culture surveillance. What they did was derived an empirical model based on rainfall data from climate hazards group infrared precipitation with station data or CHIRPS and 2-meter air temperature data from European Center for Medium Range Weather Forecast. And what they found was that the model showed a direct epidemiological association between rainfall and NTS infections. And the results are shown here. This was conducted from 2013 to 2019. And you can see that observations and model predictions, they match quite well, and time series also show a good match between NTS prediction using environmental data. Another example is from European Space Agency's EO Science for Society, and that has launched a CYAN or Waterborne Infectious Disease and Global Earth Observation in the nearshore. So they build capacity and resilience against waterborne diseases under extreme weather conditions using flooding information from Sentinel-1 and Sentinel-2 observations. We'll talk about this satellite soon, and you can browse through this website for more information. So this is another example given on EO Science for Society, that's impact of monsoon floods on waterborne pathogens in South India. So they examined extreme rain events and floods in South India using Sentinel-1 and Sentinel-2 flood maps, and they used E. coli data from in situ water samples and incidence of acute diarrhea disease. They were all co-analyzed, and flood maps from remote sensing along with maps of water quality information, showed potential to assessing risk of pathogens in water based on this analysis. And figure is shown here. This is the area where floods occurred. This is false color image from Sentinel-2, and these two are flood images from Sentinel-1 and Sentinel-2. And so this is another example how environmental parameters can be used to look at waterborne disease outbreaks. With that, we will have an overview of Earth observations relevant for inferring to waterborne diseases. As shown here, NASA has a fleet of Earth observing satellites, and many of these are useful for monitoring water quality or looking at environmental parameters such as precipitation or soil moisture or land cover, which can be used to infer to waterborne pathogens or waterborne diseases. Also, there are some new missions coming up. NISAR will be coming up soon, Landsat Next and SBG. These future missions will also help in looking at water quality as well as watershed processes and environmental parameters useful for detecting waterborne diseases. Here is a list of current satellite missions relevant for inferring to waterborne pathogens. The names are listed here. Some are acronyms which are defined on subsequent slides, and you have launch dates for each satellite mission as well. If we go through the panel, what we see is different satellites with different swaths. Their orbits are shown, and so these satellites include Landsat 8 and 9, Aqua and Terra, SNPP, JPSS 1 and 2, GPM, SMAP, PACE, and Sentinel-1, 2, and 3. These are European Space Agency missions. All these satellites can be used to derive some environmental parameter or parameters which can be used for inferring to waterborne pathogens. These satellites have multiple sensors and different swath widths, as we can see. There are also orbit gaps in between, you can see, and they all have different spatial and temporal resolutions. Another thing to note here is that other than GPM, all other satellites are polar orbiting satellites covering from pole to pole and global observations. GPM is a low inclination orbiting satellite and has 65 south to 65 north coverage. So next, here's a summary of satellites and sensors for monitoring land and water body parameters. So the satellites listed here, parameters are given here, and their spatial and temporal resolutions are provided here. All these satellites, they have either optical sensor or optical and thermal infrared sensor flying on them. So starting with Landsat 8 and 9 has OLI, operational land imager, optical, and then thermal infrared sensor, which is thermal IR. Terra, Aqua, SNPP, and GPSS, they have MODIS and VIIRS. They are optical and thermal IR sensors. Sentinel 3A and 3B, they have ocean and land color instrument and optical sensor, and SLSTR, sea and land surface temperature radiometer, that's an optical and thermal sensor. Sentinel 2A and 2B has multispectral imager, which is optical sensor, and PACE, which is the latest NASA mission, has ocean color instrument, which is an optical sensor with hyperspectral measurement capability. All these satellites provide surface reflectances in optical bands and also provide emitted thermal radiation and can be used to derive water quality parameters listed in this column. Most of them, they provide temperature, chlorophyll A concentration, sediments, and CDOM. They can be obtained from these optical sensors. And if you look at land properties, land cover can be obtained from optical sensors as well. There are standard products from MODIS and WIRS, and also from Sentinel-2 A and B. These land cover products are available. And some of these water quality parameters are also available from these satellites, as we will see later. A note about PACE has hyperspectral measurements, so not only it provides conventional water quality parameters such as chlorophyll A and suspended particulate matter or CDOM, but also has capability to provide phytoplankton community constituents, and they will be available soon from PACE. If you look at the spatial and temporal resolutions, Landsat has smaller swath, so does Sentinel-2, 185 to 290 kilometers, and MODIS and WIRS, they have broad swaths. Olchi next, and also has broader swath PACE also. You can look at the special pixel resolutions or special resolutions here. Landsat and Sentinel-2 have higher resolution, 10 meters to 60 meters, 15 meters to 60 meters here. And these three sensors, so MODIS, WIRS, and Olchi, they are medium resolution from 250 meter to 1 kilometer. And PACE also has 1 kilometer resolution. Other than Landsat and Sentinel-2, other satellites have 1 to 2 day coverage. Landsat is 16-day, and Sentinel-2A and 2B combined, they have 5-day temporal resolution. Then there are satellites and sensors which are useful for monitoring hydrology parameters. That includes global precipitation measurements. Now with GPM, that has a microwave imager and a dual frequency precipitation radar. These measurements are used to calibrate constellation of national and international satellites data with microwave radiometers and sounders to derive a integrated multi-satellite retrievals for GPM or iMerge product. That precipitation product is available at 1/10 of a degree every half hour. Then there is SMAP with L-band microwave radiometer to measure soil moisture, has relatively broader swath, and 2 resolutions are available, that's 6 kilometer and 9 kilometer, and 2 to 3 day revisit time. Then Sentinel-1 has C-band synthetic aperture radar that allows surface inundation detection or flood detection, has 80 kilometer swath, 5 meter resolution, and 12-day revisit time. In addition to the satellite data, there are Earth system models which provide weather and hydrology parameters. Global land data assimilation system and North American land data assimilation. These models, they integrate surface-based and remote sensing-based observations in land surface models and provide a number of hydrology parameters, including parameters which are not directly observable, such as runoff. MERA-2, which is a reanalysis model, uses Goddard Earth Observing System or GEOS-5 model, in which vast quantity of observational data are assimilated as shown here for different years. And this model provides state-of-the-art global analysis of weather parameters. Here is a summary of all the model parameters. MERA-2 provides weather data, temperature, winds, and humidity at half a degree by 0.667 degree, hourly and monthly timestamps from 1980 to present. These are global data, of course. And from GLDAS and NLDAS, runoff and soil moisture are available in addition to other hydrology and land surface parameters. GLDAS is available at quarter degree hourly resolution since 2000, and NLDAS is available at 1/8 of a degree hourly data from 97 onwards. Next, we will demonstrate how to search and access these environmental parameters using NASA web tools. We will see how to subset these data spatially and temporally and download either data parameters or images. We will also see how to visualize the data parameters without downloading data. So I'll start with the demonstration. Before we start the data access demonstration, I want to present a couple of examples which we will use to search and access data for. First one is algal bloom in Northern Ireland in UK. There is a freshwater lake, Loch Ness, that had an unprecedented algal bloom occurred in August-September of 2023. Sentinel-2 images and normalized difference vegetation index calculated from the imagery showed the extent of the algal bloom. Here is the lake. You can already see it looks greenish in this picture. This is Sentinel-2 image, and this is NDVI calculated from the image, and you can see that it is showing algal bloom. Analysis of the algal sample showed the presence of pathogens such as E. coli, Salmonella, Enterobacter, and Clostridium, and several types of microcysteines and cyanotoxins. And nutrient runoff and water temperature were responsible for the algal bloom as shown in this study. Another example is about algal bloom in New York Finger Lakes. Here, Finger Lakes are shown in New York State. You can see they look like fingers, and some of the lakes include Lake Seneca, Canandaigua, Skinny Atlas, and Cayuga. And there was toxic cyanobacteria bloom that spread across all the lakes between June to October 2024. The algal outbreak affected swimmers, animals, and some local drinking water supplies. And the Environmental Protection Agency warned of the risks of skin rashes and blisters if people came in contact with the water, or if they ingested. Warning was about gastroenteritis, liver toxicity, and neurotoxicity. So we will look at these two examples to search and visualize data. The first web tool we want to see is NASA Earth Data. So if you look at Earth Data portal, you will see that this is the gateway to NASA Earth observation data. This is still being populated. Not all the data are available through this website, but you can always search the data and it will point you to the right website where you can get the data. By 2026, all the data should be available from this site. You can see there is data catalog, data tools, there is data alerts and outages for various reasons. You can browse data by topic, different areas. There are featured news and events. You can look at data tools. We are going to look at a couple of them, especially Worldview. So this site is really the master site to search the data set. If you go directly to Earth Data Search, you will be taken to this data search website. You can take the tour to go through all the features, and one thing is that you have to have a username and password to access these data sets. You can log in. If you do not have, you can skip tour. And I've already logged in, but otherwise it will take you to a registration page. It's NASA Earth Data registration, and you can create an account and then you can access and download data. Of course, its data are free. You just need to register to access them. Before we search for a specific data set, you have a number of options to filter data. you can narrow your search by keywords. So if you are interested in atmosphere or say oceans, you can pick that, or agriculture, and so it allows you to narrow your search. Platforms are available. We can say space-based or land-based or other, and instruments. If you already know, if you want MODIS or VIIRS or GPM, GMI or iMerge, you can select according to that. So there are options if you already know what you are looking for, or you can just start searching with specific data set. So we can start searching data that we are interested in, and I'm going to start with the Loch Ness example. So here let's search for chlorophyll concentration, which is used as proxy for algal bloom. So you can say chlorophyll, and we can say MODIS and search for the data. You will see several matching collections. You could also see that it shows vegetation indices, it's chlorophyll over land. So to further filter, we can say ocean color chlorophyll MODIS, and then you should be able to see chlorophyll from aqua and terra MODIS, and you will see binned data, which are raw data binned. We want globally mapped data, so we can select aqua MODIS global mapped chlorophyll, and you will see a number of granules starting from 2024 December. Here we can filter it by dates or calendar. Here we know that the algal bloom in Loch Ness occurred in August-September 2023, so you can select data based on that, filter by temporally filter the data. So this is August and September, and you can apply. Now you can see that the matching granules are much smaller. Further, you can do spatial subsetting. For that, you can go to the map, and here if you zoom in, you will see this Loch Ness, and you also have latitude, longitude. You can zoom in that way also, and pick either a polygon or a circle, square, or point. I'm going to, for simplicity, I'm going to use a square here. You can have a bigger area if you're interested in watershed itself for other data sets. For example, I have picked this, and now if you look at, you will have specially subsetted data. You can either add each granule or each image map separately, or you can say download all for bulk download. Then it allows for edit options, so you can customize. You can just download all the data, or you can customize. If you have multiple parameters in this file, then you can pick variable as well. Here you can see documentation, subsetting we've already done. You can see edit variable, so here we can pick everything, and this allows us to now download data based on that. You can also see NetCDF. You can choose NetCDF and say done, and now you have picked specially temporally subsetted aqua MODIS chlorophyll data for this region for 2023 August-September. Data will be in NetCDF format, and you can download and save on your computer. Now that we already have spatially and temporally subsetted data, we can search additional data set and get the data set. So say, for example, if you're interested in looking at runoff around the lake, Then you can see GLDAS runoff. You can refer to the data tables that we looked during the presentation, and you can see which source to use. So here we are using GLDAS runoff, and you can search. There are multiple options again. This is quarter degree 3 hourly. You go down and you will see monthly data. Then there is a 1 degree data. We want quarter degree 3 hourly data, so we can pick that. One thing to note, let's pick this granule, for example, for 30th September in 2023. And if you say download, here you will see that if you look at edit options, you don't have customization options like we had for Moody's chlorophyll. So what it means is that you will have to download this entire file for this day, in which you will have variables addition to runoff. You will have soil moisture, precipitation, evapotranspiration, and other data sets. Then you will have to do post-processing to subset the data if you are interested in just one variable. And then you can just download the data. So through Earth Data Search, we saw that we can search and access data. We can do bulk download or can download individual maps or images. And almost all data sets that we want to look for, we can search, and this site will point you to where to get the data. However, if you just want to quickly look at the data, visualize the data, then there is another tool that we can use, and that is NASA Worldview. So our next demonstration is going to be about NASA Worldview. So now we will see how to visualize data using NASA Worldview. You can click on these events for information about the specific events in Worldview, but let us look at the data that we are interested in looking at. If you look at this panel, these layers, the reference layers, you can turn place labels on, you can turn coastline, borders, and roads on. These base layers are true color images from WIRS and Moody's. You can turn many off, all of them. Right now, what is showing is Terra Moody's true color image. This is for February 18th, 2025, but you can navigate through this timeline. Many data are available in near real time with low latency, such as 4 to 6 hours. And so near real time and historical data can be accessed through Worldview and can be visualized on this map panel. Add layer allows you to search for data and add to this panel. Now, one thing to note here is if you look at Moody's Aqua, for the same time, it's not showing where the Terra image was, and that is because, as we saw earlier, they all have different equator crossing time. So local time of observations are different for different satellites. They all have so different swaths cover different parts at different time, and so not all of them are coincident, but we can keep one of them on just as reference. So before we start looking at environmental parameters, other parameters, I want to show that we can add a water mask. There's a global water mask at 250 meters from Terra Moody's and Shuttle Radar Topography mission that you can select, and that shows where all the lakes are and of course oceans are. Let's go to our case study that we have been looking at. This is in UK, in Northern Ireland. This is Loch Ness, and this is the lake. You can see it's demarcated by this mask. Now we can look at chlorophyll concentration data that we searched in NASA Earth Data Search. So here we can we can search for chlorophyll, and all the options are shown here. Now paste chlorophyll is available here, but that starts in 2024 and our case study is in 2023. So let's go to 2023. This is year, month and day, and go to August when the algal bloom was noted, August and September. So let's start with August. So first of August, and now we can look at the data here. Let's pick Sentinel-3A and B Olchi data. There is NOAA 20 and 21. These are JPSS satellites. We have data from WIRS, SNPP WIRS. These are past data. Look at Aqua and Terra Modis. So if you remember the table, we have these data available from number of optical sensors, and they all can be visualized here. So we have picked them all, and you can see that there are some data showing. This is overlap of all different satellites and sensors we have picked. If you want to know which satellite is giving what value, you will have to turn this one by one off. I'm going to keep them on so that we have a better view of how chlorophyll A is changing. Now if you go to August 2, all of a sudden you see there is no data, and that is because of this presence of clouds. Most of the time when there is overcast or very high cloud cover, optical sensors cannot see through and cannot see the surface. In that case, we do not have chlorophyll data, and so we don't have for this day. If you go through the time, March here, 5th relatively clear spot over here, and then you can see that you see this chlorophyll data clearly here. You can go through this and you will be able to see that if it is really cloudy, then you do not have data. But let's go back to 5th of August when we did have data and we see chlorophyll concentration. All the yellows and reds are higher concentration, 6 to 10, and then this dark red spots are more than 20 milligrams per meter cube. So we can see this, and you can work through all the days and see when you see higher concentration. In addition to the chlorophyll in water body that we saw, as we talked about earlier, there are weather and hydrology parameters that impact waterborne pathogens, and so we can view those as well. For this case study, there was excessive runoff bringing nutrients in the lake, and that caused algal bloom. So we can look at precipitation, and so let's look at land cover also. There is Terra and Aqua Modis based annual yearly land cover type. We can add that. Then we can add precipitation, and we can pick iMerge. This is from GPM, and even we can look at soil moisture. There are multiple choices here for all parameters. I'm going through the table that we covered. Here we have soil moisture 9 kilometers from SMAP. So let's see. We can use that. This is daytime, this is nighttime. We just want to see an example, so we can select that, and we can view these parameters. So first of all, let's just look at land cover around the lake, and when you point to these squares will tell you which color means what. So this color is savannas, this is grassland, this is cropland. So you can see that all three are there, especially grassland and croplands are surrounding here. Also you can see urban areas right along the lake. So when there is runoff from these different areas, different nutrients or different debris or the chemicals, they flow into the water, and then waterborne pathogens are flourishing because of that. So you can look at land cover to see where more precipitation is in which area. And so let's look at I-merge precipitation. Now this is a half-hourly data, as we saw earlier. You can see daily data here. So if you zoom out a little bit, you can see precipitation system processing progressing in this area. So there is no rain on August 3rd. 4th, there is a system coming in, and there is more rain on 5th, and then that moves on. You can also look at soil moisture in this area, and if you navigate when the data are, when there is overpass here or when the data are there, you can see that around the lake there is moderate amount of soil moisture, a higher soil moisture in these areas, and you can look at how it is changing with time. Again, around the lake, soil moisture will also determine amount of runoff in the water, in addition to terrain. And when there is rain, if soil moisture is higher, there will be more runoff because there will be less percolation in the or infiltration in the ground. So you can look at different variables here and visually understand or try to judge a situation that's going on. You can also look at additional data such as Mehta 2 that we mentioned earlier for weather data. So temperature, wind, you can select those and display to look at the situation around the case study that you are interested in, the region you are interested in. And the advantage of this tool is that you can have many data sets in near real time. Some other features are you can share this map, you can save the link and email it to yourself or somebody else. Switch projection, take a snapshot, you can have information about the tool. Here you will see for each data set there is information about that data set as well. There is also a feature for animation. You can let's look at animation of precipitation just for example. You can select days. Here we can go from 1st to 16th, or you can even go later for this whole month, and then you can see how precipitation systems are moving through this area. You can change speed of how the rate at which the frames are moving, and this allows you to look at progression of precipitation or any other parameter that you are interested in. You can also download data. When you say download, it will show up all the layers available. Some layers, if they're not available for this particular date, then they won't be available. But as you can see, the download data will be performed using NASA's Earth Data Search, the tool that we already saw earlier. And so with that, one final tool that we want to talk about is CYAN, which allows us to monitor cyanobacteria bloom in the lakes in the US. So let's start with Cyanobacteria Assessment Network demonstration, or CYAN. This is a web application. CYAN is a joint project between EPA, NASA, NOAA, and USGS, and it focuses on cyanobacteria density or concentration in lakes in the US. Just a note here, ARSET conducted CYAN training earlier, and you can view a YouTube video at this link, provides detailed information about CYAN. Let's go to the website here, and you will be asked to either create new user information, or if you already are a user, you have a username and password, you can log in and start using CYAN. This is the main page of the application, and you will see that there are a number of options here. My locations. Locations we pick through this marker. We can just click on any water body and then that puts a marker there. Let's come back here later, but there is water body stats. You can search for a water body and get cyanobacteria statistics. There are options here. You can have a street map, or you can have imagery, and you can also highlight water bodies or look at the outline of all the water bodies that are covered. This data, cyanobacteria data, it's coming from Sentinel-3 Olchi data, and so from 2016 these data are available. As we saw earlier, Olchi has a resolution of 300 meter by 300 meters squared. That's the pixel size. So lakes which are bigger than at least 3 pixels of Olchi, that means 900 by 900 meters square or bigger, those are seen by Olchi and they are included in CYAN. You can zoom in on the map by using this plus sign or with your mouse, and you will see that there are markers which I have picked here. This is Lake Erie, and then these are Finger Lakes. We can zoom in further to the Finger Lakes region, and these are the Finger Lakes. This is Lake Seneca and this is Lake Cayuga, and you can see that there are 2 markers that I have placed here earlier. You can click on any location, any water body, and it will place a marker there. You will also see that they have, these markers have different colors, and to see what they mean, you can go here and see the marker color configuration. What they show is that location cyanobacteria density in cells per milliliter, if it is lower than 100,000, it is green. If it's between 100,000 and 300,000, it's medium, and so then it's high. And so these are the ranges, but you can also change this range, and if you update it, then colors also change accordingly. So you can also decide how you want to define the thresholds, and so that's what the colors show here. If you go to my locations, you will see that wherever you have put markers, those locations will show up. I have one in Lake Erie also, but this one is in Seneca Lake and this is in Cayuga. Let's focus on this one. It provides information about the point where the marker is. It shows cells per milliliter and also change in cells per millimeter since this, and this is the image for which the data are there. So one more thing you can do is, if you select this, it provides overview. That means all the Sentinel-3 Olchi images available which have overpass over that location, that pointer location, they will be here. You can see slideshow. You can download this as TIFF images as well, and for each image you will see cyanobacteria concentration in here. If you click on the chart, it shows chart for cyanobacteria concentration, and this starts, so whenever there are images and they're able to cover that marker and it's cloud free, then you have data. And as you can see, in 2024 you do see increase in cyanobacteria concentration in September, October of this year, which had health implications as we saw earlier. This chart is just for this pointer location. If you want to see the statistics for this entire lake, then you can click on this symbol. It opens this panel with water body information, Seneca Lake in New York State, coordinates, area and elevation. You can look at daily histogram for a single date, or you can have 7-day or 30-day history of cyanobacteria concentration. Let's pick 30-day history and select end date in 2024. I'm going to select September 30th so we can look at the entire month of September. So whenever there is satellite data available, satellite overpass from Sentinel-3 is available, and when there is algal cyanobacteria bloom going on, then you will have information. So here, based on that, you have two charts. This is total cell count. These are Olchi pixels, number of pixels. And for these dates, when there was a cyanobacteria bloom and when satellite could observe it, you have data that how many pixels had low concentration, how many pixels with medium, high and very high concentration. You can see that. It's the same information provided here, but now it's broken down by range. So you can see time series of how many pixels in low cyanobacteria concentration range, then middle and high and very high range. So you can see the history of cyanobacteria bloom over the lake over this month. You can also see slideshow. So you can see special distribution where you see cyanobacteria bloom, and whenever you see the bloom and also at the same time you have satellite data going over it, you will have information here. So for here, this is 14th of September. So if we go there, we should be able to see an image right there. You can see cyanobacteria bloom over there. It works through the history and shows whenever and wherever in the lake there was cyanobacteria bloom that satellite can observe. So based on this, you can pick the lake of your interest and look at the algal cyanobacteria bloom, and then you can go back to Worldview and look at other environmental parameters around the lake of your interest. So with that, we conclude the CYAN demonstration. Just a note here that if you click here, you will have documentation about CYAN and about this website and web app. There's also a mobile app that you can use, but all that information you can find here. So in summary, today we reviewed common waterborne diseases and pathogens, identified environmental parameters relevant for inferring to the presence of pathogens, introduced satellites, sensors, and Earth system models to obtain the environmental parameters, and finally demonstrated web tools to access satellite and model data and to monitor cyanobacteria bloom in selected water bodies in the US. We looked at NASA Earth data search and Worldview for data access and analysis, and we looked at CYAN web app to look at cyanobacteria concentration in selected lakes in the US. A note about advantages and limitations of using Earth observations for monitoring waterborne diseases. We saw that not all waterborne pathogens other than algal bloom are directly observable from satellite data, but there are various environmental parameters which are observed, and they provide valuable information about waterborne disease risk. These parameters include precipitation, water temperature, soil moisture, runoff, etc. Earth observations complement sparse and infrequent in situ data. They are regular and consistent observations over large areas with consistent spatial and temporal resolutions. And a wide range of free and open access data products are available, as we saw. Some of the limitations are that various satellites and models, they provide data with different spatial and temporal resolutions and coverage, have different characteristics. So it is important to understand their characteristics and select data sets that's ideal for your area of interest, so region of interest. Optical observations cannot see through the clouds, and so surface is obscured when there are clouds present, so we cannot see the surface. So there are data gaps because of that. Data extraction and processing are required for developing waterborne disease prediction models, and that is what we are going to see in our next session. On 27th of March, we'll have part 2, and we will have guest speakers presenting case studies showing model development for predicting cholera outbreak using Earth observations. There will be one homework posted on 27th, and it will be available through the training webpage. It will be submitted via Google Forms and will be due on 10th of April. Those who attend all live webinars and complete the homework assignment by the deadline will receive a certificate of completion. Email will be sent with the certificate approximately 2 months after the training is over. With that, we want to thank everyone for joining today's session, and want to thank our coordinator Natasha Johnson Griffin, our editors Susan Monty and Jonathan O'Brien, ARSET coordinators Brock Blevins, Sarah Cutshall, and Selvin Hudson O'Doy. This is ARSET website link here, and here is our social media presence if you want to check it out. So with that, thank you so much for attending today's session, and we will go to the question and answer session now. Thank you all for attending this session, and we have received several questions, so we will work through the questions here. We'll start with question 1. Is the key issue sewage contamination or wastewater treatment for the US waterborne illness impacts? It is one of several factors, as I understand, but not just the key issue for waterborne diseases in the US. There are urban, industrial, agricultural runoff, they all contribute to growth of pathogens in water bodies. So it may depend on which region you are considering or which water body you are looking at, and then these factors may contribute in different capacity for that particular water body. Question 2 is, can unusually low dissolved oxygen be quantified with remote sensing? So dissolved oxygen does not change optical properties of waters. So directly, if you look at satellite image, you will not be able to say whether there is decrease or increase in dissolved oxygen. However, it can be inferred from other parameters, such as if you have more chlorophyll concentration, then it would cause hypoxia or decrease in dissolved oxygen. Or there are really biogeochemical models which you can use based on processes, biogeochemical processes, to derive dissolved oxygen concentration in water body, and will provide you some references for that. This has been done for regional water bodies, especially for estuaries, it's been done. Question 3, is there a scale to rank a region's wastewater's mitigation, remediation, treatment success? I do not have expertise in this topic, but just by looking at some of the literature, what we see is that if you monitor water quality, the plumes, if you monitor around the wastewater treatment plant, then it can give you some idea of how to mitigate, how wastewater treatment is changing water pollution nearby. And again, there are some examples that we can provide. They're published in published literature. So it has been used. It's something that I'm not my expertise, so I'll provide you some references there. Question 4, are there additional hyperspectral imaging instruments on the ISS? So yes, EMIT is a hyperspectral imaging instrument on ISS. That's currently, I think the website about EMIT is down, but I'll provide link to learn more about EMIT instrument. There is also a European or Italian instrument, it's called Prisma, that also has hyperspectral information. I will try and get all the links for you in the document when we post it. Question 5, is there a specific definition or range for thermal pollution in regards to wastewater that is discharged? So there are a number of research studies you can find. They're looking at thermal imagery, and it can be used to monitor thermal pollution, mostly if it's cooling or heating water due to either industrial cooling or that will warm the temperature or cool the temperature if there's discharge in a water body. So I think range would be water body specific, and what kind of discharge you're talking about, that will also decide what range to look at. One thing to do is, if you look at Worldview and search for sea surface temperature, you will be able to see sea surface temperature anomaly in Worldview from multiple satellites, and you can monitor that around the area of your interest or water body of your interest to see if changing temperature is giving you any indication of wastewater discharge. Question 6, is it possible to animate average rainfall pattern over a specific period? So Worldview can help in animating images, but there is also another tool, it's called Giovanni, that allows you to look at average precipitation and can animate that, and we will provide link for these tools. Question 8, is it possible to develop a real-time application utilizing these platforms to notify individuals about waterborne disease? If so, how? Please provide me with some directions. So that is precisely what we're going to do in our next session, that we're going to use a case study for cholera, and we have subject matter experts, people who have developed cholera prediction models based on Earth observations. So they are going to show how it can be done. So it's combination of environmental parameters, remote sensing imagery, and also water sample analysis and disease incidence information, all can be combined. Socioeconomic factors and wash conditions can also be examined to come up with better risk assessment for a particular disease. So next session should help in that subject. So one comment here about that you can use the data sets we showed in the tables in the presentation as reference, and you can use either combination of these data sets or look at any one depending on the size of the water body you are interested in. And you can pick both satellite data as well as model data based on the area of your interest or water body of your interest, and any particular uh, issue, such as if there is a wastewater plant that has discharge in the water body, you can look for true color imagery, start with that and see if there are plumes you can see. You can look at sea surface temperature or water temperature to see if there is any change in temperature. Or if you're in area where there is a lot of agricultural runoff and nitrogen and phosphorus are washing in a water body, you might have a lot of algal bloom, so you can focus on that. So depending on the issue and the water body of your interest, you can pick the data set and parameters that you want to look at. Specifically for risk assessment for a specific disease, we will walk through the procedure in next session, how to develop a model or an empirical scheme to come up with a waterborne disease prediction. If you have any questions, you can still add to the question and answer document. If not, we will see you on Thursday, which is day after tomorrow, on 27th of March. So hope to see you in the second session of this webinar. Thank you, and thanks to our ARSET team. Natasha Johnson-Griffin, Jonathan O'Brien, Selvin Hudson-Odoi, Brock Blevins, and Susan Monty, Sarah Cutshell. Everybody helped in putting this series together. So thank you all.